So, electronic design automation, this is the subject we will be talking about in the course of the next series of lectures. Before I go into the actual series of lectures, let me first tell you what exactly we intend to cover in this series of lectures. Well, electronic design automation, as the name implies, what it really means is that we have some kind of a design which we want to carry out. Starting from the specification, we want to arrive at the final design implementation. It can be an FPGA, it can be an ASIC, it can be anything. So, let us first try to have a quick look at what are the topics that we intend to cover in this course. First, of course, we would be looking at the digital circuit design flow, which means that if we have a digital design, digital circuit specification, what are the different steps that you need to follow in order to arrive at the implementation. Well, out here we will be considering only digital circuits, we would not be considering analog designs. Next, we would be looking at one popular hardware description language, namely Verilog. This description language we will be using as our vehicle in some of the future lectures. All examples we will be giving in Verilog. Next, we will be talking about some topics on logic synthesis. Now, assuming that you are already familiar with two-level logic minimization, we will be starting from that point onwards. We will be talking about multi-level optimization, a process called technology mapping, and of course, something called high-level synthesis. Well, in high-level synthesis, we are trying to arrive at a design, a register transfer level design starting from a behavioral specification. Then of course, we will be considering or talking about a very important issue, that once we have designed the circuit up to a particular level, how do we test it? So, some issues related to testability. And at the very end, we will be talking about physical design automation, which concerns the issues that comes in at the last phase of the implementation, namely here we talk about the floor planning, placement, routing. These issues are arising when we consider the silicon floor. The silicon floor, how do you place the different components on the floor of the silicon, how do you interconnect them? These issues would come in here. Okay. So, let me give you a list of some references. Of course, this course is so diverse, it is not possible to specify one or a very few books to cover all of them. So, I have got a comprehensive list of references, you can have a look at these. So, the first three references would be concentrating on the design and synthesis aspects. The fourth one would talk about the Verilog description language. The fifth one is again synthesis. This concerns high level synthesis. Then we have some more references. There are two books which I have referred here for testability analysis, testable design, and the last three books are concerning physical design automation, placement, layout, routing, etc. Okay. So, during the course of this course, we would be referring to these books as and when required. Okay. So, to start with, we begin by talking something about digital circuit design flow. Okay. So, we look at the digital design process from the perspective of a designer. Now, as you know that with the advent of the VLSI technology, nowadays the complexity of design is being increasing very rapidly over the years. Now, today it is possible to have chips which can house more than a million transistors, multi-million transistor systems are possible on a chip. So, design complexity is growing. Design complexity has two you can say two dimensions. One is of course the increased size and the increasing complexity to handle a design of that size. Okay. Now in earlier days when the designs were small, many of the designs could have been done using some kind of manual technique or semi automated technique with frequent manual intervention. But what has happened today with the increasing size of the designs is that nowadays it is absolutely essential to have computer aided design tools to assist the design process. So that without the computer aided design tools you really cannot handle a design of that complexity. So if you look at the way a designer proceeds with designing a typical chip or a circuit nowadays, there is a conscious effort to standardize the design flow. Design flow, as I had mentioned just previously, it is basically the process which you follow starting from the specification down to the implementation. What are the different intermediate steps? Now depending on the kinds of CAD tools you have, depending on the kind of chip you are trying to design, the design flow can vary quite widely. So it is essential or necessary to standardize the design flow before you are actually trying to design the chips. So just as I mentioned, design flow is essentially the design procedure, stepwise procedure which you follow starting from the design idea or specification, whatever you call, down to the actual implementation. Now actual implementation, when we are talking about, well, again I have told you this can be an application specific integrated circuit, it can be a field programmable gate array, or it can be any other kinds of programmable logic like PLDs or any other thing. But the idea is this: you have a design idea which you specify in some form, and using a sequence of steps using the CAD tools, you finally arrive at the actual implementation at the very end. Now out here I show a few of the steps which are followed. There are a few more steps also. Of course, the first step is the design specification. Then you carry out synthesis, which is essentially a design translation from the specification to some kind of a netlist, some kind of a register transfer level or a gate level design. Then you typically carry out simulation to check whether this synthesized design is correct or not. There can be some problem with the CAD tool also. You must be 100% sure before you actually go for the implementation or the manufacturing of the chips. Okay. Now the simulation can be done at a number of different levels. This we'll be looking at in some more detail later, because you can also decide to do the simulation after specification itself in order to check whether the specification is correct. You can do the simulation after synthesis. Well, after the synthesis, the step after that is typically layout, where you are thinking about how to place the blocks you have synthesized onto the floor of the silicon, or in case of FPGA, well, how to place or map the sub circuits into the basic cells of the FPGA. Okay, so these are the layout concerns. Now during synthesis and layout itself, you often also consider some issues related to testability. This means when you are designing the circuit, well, the circuit is functionally working correctly or not, that is one issue. The design is correct or not, that of course is a very big issue. But after manufacturing there can be a number of defects. There can be some short circuit in the wires, there can be open circuit, there can be a lot of other problems in the transistors. So after manufacturing you have to test the chips. Now here I have just told you that you today have chips which can house millions of transistors, but externally you can have only a few hundred pins available to you. So just using those few hundred pins, how do you test those million components inside? there has to be some special design effort that has to go in during the synthesis process itself, so that during testing it becomes easier for the test engineer to test the chip. There are a number of techniques called design for testability, built-in self-test. These are the things we'll be discussing. And there are
what did you say, that the design process are such that the testability can be made easier?
Okay, that exactly what I've said is that designs are big nowadays. So unless the designer puts in some special module, some special design, you can say design procedures or design rules in the process of synthesis, it may become impossible for the test engineer to test the chip. Just if I give you any arbitrary chip and ask you to test it, it can become a very big problem for you. But if during the design process itself I have incorporated some feature in the chip, just using which you can test it easily, it can become very easy for you for testing. Okay, fine. Now, as I had mentioned that with the increased size of the chips and the increasing complexity, the CAD tools are essential. There is a new generation or a new series of CAD tools which is now available in the market, which are used by the designers to go through the digital design flow process. Now, all these tools are based on some so-called hardware description languages. Well, hardware description language means you have a standard way of specifying things. That thing may be your design specification, that may be your synthesized netlist, that may be the layout, it can be anything, but you have some standardized formats in the form of some language. Well, basically this hardware description language, they provide ways of representing the design at several different levels. Okay, this we will see later that how. So I mentioned as we go through the different design steps, your design goes on refining from the behavior to register transfer level to gate level to layout. Now, if at each level you can represent the design properly using a description language, it becomes a consistent format. Well, here one advantage you gain additionally is that if you follow some standard, your internal representation may be portable across different CAD tools from different vendors. Say that one part of a design flow you can do using the CAD tool supplied by vendor A, the other part you can do using a CAD tool supplied by vendor B. So if you are following some standard, then you have complete portability and interoperability. Okay. And typically, as I had mentioned, as you go from top to down, from the behavior down to the layout, you typically go through a series of transformational steps where each succeeding step will contain more detailed hardware implementation, or means hardware information as compared to the previous level, from behavior to register transfer level to gate level to transistor level, and so on. So these are some of the typical steps of transformation: behavioral to RTL, RTL to gate level to transistor level, then finally you can have another level, transistor level to the final layout, geometries of those layout, the layers. Okay, fine. So let us first talk about the hardware description languages.